We have spent many videos to talk about the work energy theorem, and we have spent even many more videos to talk about the fact that the work done by conservative force is equals to the negative of the change of potential energy. So now this video here will be the point where we harvest the fruit of that we have been nurturing over the many videos previously. To be more specific, we are going to relate these two equations here to create a new principle of conservation called the principle of conservation of mechanical energy. So we relate these two equations here, and I'll relate it using a few situations. So let's start with situation 1. Situation 1 is a situation where we have a block sliding down a frictionless inclined plane. So we have a smooth inclined plane, and we place a block on top of the smooth inclined plane, and now the object will slide downwards, thus undergoing a displacement where we call S. So now if we try to study the work done by the various forces acting on this object here, we will have to start by drawing the free body diagram to show all the forces that are acting on this block over here. So let's try to draw the free body diagram. Well, our free body diagram will be inclined. The axis should be inclined following, we have one axis parallel to the inclined plane, one axis perpendicular to the inclined plane. So this dot here is representing this block. This block is our object of interest. So we know that this block has mass, therefore this block here will have a weight, which is a gravitational pull exerted by Earth on the block. Then we also know that this block here is touching this surface over here. Thus, this object here will experience a normal force perpendicular to this surface. And we know the direction of normal force should be pointing in this direction, right along the y-axis. Okay, so this is the free body diagram, and we are having a smooth surface, so no friction. We have no ropes, no strings, so no tension, and we have no force being explicitly stated, so no external force. That's all that we have for our free body diagram. So we know that our work done total here, our total work done here is composed of the work done by gravity, which is the work done by the weight, and the work done by the normal force. So we can substitute the work done by gravity and work done by normal force to represent the work total that we have here. So this is a substitution that we are going to make. We equate these two equations here. So right now the work done by gravity and the work done by normal force is equals to the change of kinetic energy. So at this point, right, one should notice that this normal force here and this displacement here are perpendicular to each other. The displacement is parallel to the x-axis, whereas the normal force is parallel to the y-axis. They are perpendicular to each other. So if you are finding the work done by this normal force over here, you should expect that the angle between the normal force and the displacement to be 90 degrees. And since they are 90 degrees, we know that trigonometry says that cos 90 degrees equals to 0. Therefore, the work done by normal force will be equals to 0 joule. So what happens here is we replace work done by normal force with 0 joule. Thus, we are left with only work done gravity equals to change of kinetic energy. There's no longer any work done due to normal force. This will be replaced with 0. So now we have work done gravity is equals to change of kinetic energy. So right now, our total work done is only the work done by gravity. Means by the work done by gravity is it's all the work done that we have acting on this object here. So gravity is the only force doing work on this object over here. So if that's the case, we now will relate this work done by gravity with the idea that work done by conservative force is equals to the negative change of potential energy. To be more specific, we will say that work done by gravity is equals to the negative of the change of gravitational potential energy. So now if we substitute this negative change of gravitational potential energy to replace our work done by gravity, now this will be the new equation, where now everything is expressed in terms of energy and there is no more work done in the equation anymore. So this is very important because I'm going to expand it to show that something interesting is happening. So we know that delta here is just final minus initial. So we can expand this delta potential energy here as the negative of the final gravitational potential energy plus the initial gravitational potential energy. Remember, this is final minus initial, so minus final minus minus plus initial. Whereas on the right hand side, we have our kinetic energy final minus kinetic energy initial. So now you might not see the pattern yet, but let me rearrange the terms we have in this equation. Let me bring everything related to initial to the left hand side and bring everything related to final to the right hand side. To be more specific, I shift this first term here, the final gravitational potential energy, to the right hand side of the equation, and I shift this initial kinetic energy to the left hand side of the equation. Now you see the left hand side of the equation is just the initial kinetic energy and the initial gravitational potential energy. Whereas on the right hand side of the equation, it's a final kinetic energy and the final gravitational potential energy. Now here's where we bring in a definition of mechanical energy. Mechanical energy is the sum of kinetic and potential energy. So this is the sum of kinetic and potential energy. Therefore, these two terms here will form our mechanical energy. To be more specific, the left-hand side will be the initial mechanical energy. The right-hand side will be the final mechanical energy. So now what am I trying to imply here? I'm trying to say that if gravity is the only force doing work on an object, through this series of derivation, you see that the mechanical energy initial will be equals to the mechanical energy final. Thus, the mechanical energy of the system remain constant, or we can say the total mechanical energy is conserved. So again, the conclusion I'm trying to make here is if gravity is the only force doing work on an object, the total mechanical energy is conserved. Okay, so now let's move on to the second situation. Second situation, we will consider a situation where a block is dropping onto a spring. So this example here, we have encountered it in the earlier video when we talk about work done by the restoring force of a spring is equals to the negative change of the elastic potential energy. If you're not sure what does this example means, please refer to the video where we discussed about this earlier. So what I'm trying to show you here is we have our initial position where the spring is being compressed by x initial, and this object moves downwards with a certain displacement, reaching its final position. Now at this final position, the spring is compressed by a distance of x final. So this is the situation that we have. So now if you draw the free body diagram of the object, we see that this object here is experiencing weight because this object here has mass. Therefore, this object experiences a gravitational pull by the earth. But at the same time, because this object here is touching the spring throughout this journey, you should expect that there's a force pushing upwards by the spring on the block over here. So you should expect this force pushing back by the spring on the block to be the restoring force of the spring. So the spring, because it wants to revert to its original length, it will try to push upwards. And that upward push experienced by the block here, it's what we call as the restoring force of the spring. So if you consider the other questions, whether there's any rope, strings, or cables, whether there's any rough surface, whether there's any surface touching it, you see that these are the two only forces that are acting on this block throughout this journey over here. So if that's the case, right, for our work done, our total work done here will be consists of work done elastic, which is the work done by the restoring force of a spring, and the work done by gravity, because those are the only two forces that are acting on this object here. So the sum of these two work done will form the total work done. Okay, so right now, be very clear that what are the forces acting on the object are the gravity and the restoring force of the spring only. And if you remember, these two forces are actually conservative forces. And when these two forces are the only forces acting on the object, something interesting will happen as well. So we know that work done elastic here, we can replace it with the negative change of elastic potential energy. Whereas the work done by gravity here can be replaced with the negative change of gravitational potential energy. So now if you replace this work done with change of energy, you see that the new equation form will be the negative change of elastic potential energy minus the change of gravitational potential energy equals to the change of kinetic energy. Now we have completely eliminated work done from the equation. We have replaced everything to be expressed in terms of energy now. So again, we do something similar to situation 1. We will expand the delta here to become final minus initial. So this is the equation we have. We break it open. We have our final elastic potential energy minus the initial elastic potential energy. That's what it means by this delta over here. So we minus bracket the delta U inside here minus bracket the delta U subscript G, which is the gravitational potential energy final, minus the gravitational potential energy initial bracket. Then our delta K is final kinetic energy minus initial kinetic energy. Now you might need to take a piece of paper and try to rearrange it yourself. So what you need to do is bring initial to the left hand side of the equation and bring all the final to the right hand side of the equation. Then you end up with this equation over here. The kinetic energy initial plus the elastic potential energy initial plus the gravitational potential energy initial is equal to the kinetic energy final plus the elastic potential energy final plus the gravitational potential energy final. Well, again, what's happening on the left hand side? That is just mechanical energy initial. What's happening on the right hand side? That is just mechanical energy final. So here we have also arrived at a similar conclusion. If gravity and restoring force of the spring are the only forces doing work on an object, then the total mechanical energy is conserved. Now I hope you are seeing a pattern right now. The pattern that I'm trying to lead you to is, if situation 1, we have a conservative force being the only force doing work on an object, we see that the total mechanical energy is conserved. Situation 2, we have multiple forces doing work on an object, but those work are all done by conservative forces. As long as all the forces doing work are conservative forces, you see that the total mechanical energy is conserved. So the conclusion that I want to make here is, if conservative forces are the only forces that are doing work on an object, if you look at the work total and all the work that is being done on an object is by conservative force, we will know that the total mechanical energy is conserved. And this is the principle of conservation of mechanical energy. To express it in terms of words, the total mechanical energy of an object remains constant as the objects move. Okay, the total mechanical energy is conserved, the total mechanical energy remains constant as the object moves, provided, so this is the criteria for mechanical energy to be conserved, provided that the net work done by the external non-conservative forces is 0, or the work done by non-conservative forces equals to 0. Well, it's actually almost a similar thing, right? If you want your non-conservative force to do no work, that means you can only have conservative force that do work on an object. So these two actually have similar meaning, slightly different, but they share a similar idea that if you have 0 work done by non-conservative force, then your total mechanical energy is conserved. And that's the fruit that we are harvesting right now. If we properly understand the work energy theorem and the fact that work done by conservative force is equal to the negative change of potential energy, if you understand these two equations properly, we are able to derive the idea of principle of conservation of mechanical energy. Okay, so if conservative force are the only forces doing work on an object, the total mechanical energy will thus be conserved.